it will return a random number between 1 and -1. For example, a 2D example of this would look like this, where any given x value gives a pretty much random output. However, it's extremely important that this noise function always gives the same output value for a certain input. So in this example, an x value of 3 gives an output of 0.5, and although that 0.5 is a completely random number, it mustn't change. Anytime that we put an x value of 3 into this function, it returns 0.5. We can still have different noise functions every time we run the game, but once the game is running, the noise function mustn't change because the height of the terrain vertices shouldn't be changing. So it's the same for our noise function here. If we put in the values 5 and 14 for x and z, it will return a random output, but any time that we put in 5 and 14, it should return the same random value. Now, the way that I've implemented this is perhaps not a very nice way of doing it, and if anyone knows a more elegant way of doing this, then please let me know. But what I'm going to do is to set the random based on the x, z and seed values, and then return the first random float that it generates, which would be a number between 0 and 1, so I'm going to convert it to be a number between -1 and 1. So for any given x, z and seed values, this would always return the same value, because the seed of the random would always be the same, and it always returns the very first float. However, I found that similar seed values return similar first floats, which means that neighbouring x and z values would actually give very similar outputs, and the terrain wouldn't appear very random at all. So I'm just going to multiply in a few big numbers here, so that even a small change in the x or z values would cause a completely different seed to be used. You don't want to make these values too high though, otherwise you risk creating a seed whose value is greater than the maximum int value in Java, which would obviously crash the game, and that's the same reason why we didn't set the seed variable too high. Let's now just test that we've got this working, so in the constructor I'm going to print out the value generated when the inputs are 5 and 14, and I'm then going to copy and paste that to make sure that it gives the same output when the same inputs are used. And then we'll test it one more time with slightly different inputs. So let's go ahead and run that and see what we get. So if you have a look down in the console, you should get two random numbers that are exactly the same because they had the same input, and then a third number which is completely different, even though there was just a slight change in the inputs there. So let's now just get rid of these tests, and we're now going to use the getNoise method as the output for the generate_height method. So every vertex is going to have a completely random height between -amplitude and amplitude. So if I run that, you can see it's going to get pretty crazy with a lot of random vertex heights. So at the moment, our terrain is clearly extremely random and extremely rough. So what we're going to try and do now is to make it at least a little bit smoother. The way that we're going to do this is that instead of setting the height of each vertex to the output of the random number generated as a coordinate, we're instead going to calculate the height based on the average of the random number generated output for that vertex and all neighbouring vertices. This is exactly the same concept as you would use in an image smoothing filter, which, as you can see, makes the output look just a little bit less random. So let's now implement this in the code, and we're going to create a new method here called getSmoothNoise, and this still takes in the x and z position of the vertex, and it returns the average height for that vertex. So first we're going to get the values of the corners, the outputs of the getNoise method for all the corners. So there are 4 corners, so 4 getNoise methods, and these corners are going to have the least effect on the output, so I'm going to divide them by 16. Then we need to put in the vertices, the coordinates of these corners, so that's x minus 1, z minus 1, and there's x plus 1, z minus 1, x minus 1, z plus 1, and the final corner has a coordinate of x plus 1, z plus 1. So that's the values for the corners. Now we're going to get the output of the getNoise method for all the side vertices. So again, 4 side vertices, 4 getNoise methods, and these are a bit more important, so I'm only dividing them by 8. Then the coordinates are x minus 1, z, x plus 1, z, x, z minus 1, and x, z plus 1. So that's all the sides done, and now the final vertex is the one in the middle. And this, of course, just has a coordinate of x, z, and it's the most important, so now we're going to divide it by 4. And then the total output is just going to be the values for all the corners plus all the sides, plus that centre vertex, and that's the smooth average output for all the nearby vertices. So if we use the method and run it, you can see there's a little bit of an improvement. There's a bit more structures in the terrain, and it's not quite as crazy and as random as it was before.
Insufficient funds.
What we've done so far is to create a function something like this, where for any integer input value, our function returns the x value. Up until now, we haven't really worried about what happens between these points, because so far we've only been using integer values. But what we're going to do now between the points, so that we can use float inputs, like 3.6 for example, and we would still get an output. There are various methods which we could use to interpolate between 2 points, the easiest of which would be linear interpolation, but that doesn't really look very natural, so we're going to be using cosine interpolation, which basically creates a cosine-like curve between every 2 points. So let's start off by creating a method to carry out cosine interpolation on 2 float values. So we've got float A and float B, we're going to interpolate between the 2 of them using the blend factor, and it's basically going to be like linear interpolation, except the blend factor first gets put through a cosine function. So we're now going to do a cos function to use the new blend factor, f here. So we're going to carry out the cos function, which will return a value between -1 and 1. By doing 1 minus that, we're going to get a value between 0 and 2, and by multiplying that by 0.5, that will give us a value between 0 and 1, just like the original blend factor would have been. And now that we've got that, we can just carry out usual linear interpolation with this new blend factor. So it's just the usual formula. So A multiplied by 1 minus f plus b multiplied by f. So let's now create a new method called get interpolated noise, and this is going to take in a float x and z position and it will return the height based on the interpolated height from the 4 nearest points in the noise function. So first we need to calculate the integer part of the x value and the integer part of the z value that's before decimal points. And we also need to calculate the fractional part of the x value and the fractional part of the z value. So that's the part after decimal points. You can see the top right corner. Now that we've got those values, we are able to calculate the height of the nearest 4 points in the noise function to this xz position. So we're going to get the height of the points b1, b2, b3, and b4, as you can see in the diagram in the top right corner there. And to get the height of those points, we're going to call the get smooth noise function. Then we're going to put in the necessary values. So b1 is just int x int z, b2 is int x plus 1 int z, b3 is int x int z plus 1, and b4 is int x plus 1 int z plus 1, as you can see in the diagram. Now we're going to interpolate between b1 and b2 and then b3 and b4, and this is going to calculate the height at 2 new points, I1 and I2. And now that we've got the height of the points I1 and I2, we can interpolate between I1 and I2 to find out the height at the xz position. So we're going to interpolate between points I1 and I2, we're going to use the frac z value as the blend factor, and that will give us the height of that xz position. So let's now use the get interpolated noise instead of the get smooth noise, and go ahead and run that. And at the moment, it doesn't seem like that has changed. It actually looks exactly the same as before. The reason that there's no change yet is that we're still just putting in integer inputs, so we're still just getting values and points out, and the interpolation between points is irrelevant. But if we were to divide all our inputs by 4 and then put them in functions, we'd start to see some of those interpolations. So let's try that now in the code and divide both of our inputs by 4f. And now when we go ahead and run the game, we'll see that we're starting to see a little bit of an improvement. The more we divide our inputs by, the more we start to see those smooth interpolating curves in our output. So you can test this out in your code by trying out the numbers here. So I'm going to try and divide by 8 now, and if I run that, you can see that the train is now extremely smooth. So the higher the number you use to divide our inputs by, the lower the frequency of the function's output. And by frequency I'm referring to all frequencies in waveforms, where the frequency rises and the wave goes up and down. And it's the same for our height generating function here. So when we don't divide our inputs, we get a high frequency output where the terrain goes up and down a lot. But as we increase the dividing number, our output becomes much lower frequency, with the ups and downs being much more spaced out. So I'm going to stick with dividing the inputs by 4 for now, because I think it's output, but it's a little bit too smooth at the moment, and perhaps it doesn't look quite that natural. Our terrain at the moment looks something like this, whereas a more realistic terrain will look a little bit more like this. Although the overall shape of this terrain has a low frequency, you can see that it definitely has some high frequency components in there as well. So to make our terrain more realistic, we're going to generate another noise function, which is twice the frequency of the first one. We'll then make the amplitude of this new function smaller, just by dividing the outputs by some number, and we'll then add it to the first function. So now our output will have an overall low frequency shape, but it also has some smaller high frequency components as well. So let's try this out in the code now. Firstly, we're going to create a float called total, which is going to keep track of the overall output. And to start with, we'll just set that to the output of our original noise function. We're then going to add to that a second noise function, and we want this to be double the frequency of the first one, so we'll halve the dividing numbers here. And we also want to make the amplitude smaller for this higher frequency function, so I'm going to divide the amplitude by 3. And we aren't just limited to one extra noise function, we can actually use as many as we want. So I'm going to add another noise function here, which is again double the frequency, and again 1/3 of the amplitude. So let's go ahead and run that, and you can now see that the terrain is looking pretty nice now, with both high and low frequency components. The final thing that we're going to want to do this week is to create a general version of this so that we can easily change the number of noise functions and things like that without having to actually alter any of the code. There are a couple of things that can affect the generation as well as the amplitude, and we're just going to create some constants up here for them. So firstly, there's the number of noise functions that we want to use, and these are actually also known as octaves, and I'm going to set this to 3 octaves for now. And then there's the amount that we decrease the amplitude by for each higher frequency octave, and this ends up basically being how rough the terrain is. I'm going to choose a value of 0.3 here, so that each octave will have an amplitude of 0.3 times the amplitude of the previous octave, but you can choose whatever value you want. Finally, you just need to create a general version of this method, and I've made an example one here which you can copy down if you want, or you can download the source code from the description. So that is pretty much it. You should now be able to generate some very nice looking random terrains, and you can play around with the amplitude, octaves and roughness values until you get a terrain shape that works for you. You can also use this system with multiple terrains if you want, and in the description I've provided a slightly improved version of the heights generator class which you can use to do just that. So the only changes that you have to make are that when you create your heights generator for each terrain, it needs to take in the grid X and grid Z coordinates of the terrain. It also needs to take in the vertex counts that we set earlier, and it needs to know the seed, and this seed must be the same for all of your terrains to make sure that they all use the exact same noise function. So that is it for this week. Next time we're going to be making a start on shadows, and that video should be out in 2 weeks' time. But yeah, thank you guys very much for watching this video. Do subscribe if you haven't already. Have a fantastic week, and I will see you all next time.
Hello, Discover Card here to explain our cashback match. We match all of the cashback you earn at the end of your first year, automatically. It's that simple. Discover. Exceptionally common sense. Learn more at discover.com/match. Limitations apply.
Hey everyone, and welcome to this Python and OpenCV course. In this course, we'll be talking about everything you need to know to get started with OpenCV in Python. We're going to start off with the very basics, that is reading in images and video, manipulating those media files with image transformations, and how to draw shapes and put text on those files. Then we're going to move on to the more advanced parts of OpenCV, that is switching between color spaces, bitwise operators, masking, histograms, edge detection, and thresholding. And finally, to sum things up, we'll be talking about face detection and face recognition in OpenCV, so how to detect and find faces in an image, and how to recognize them using inbuilt methods. In the last video, we'll be building a deep computer vision model to classify between the characters in The Simpsons based off some images. All material discussed will be available on my GitHub page, and all relevant links will be put up in the description below. So if that sounds exciting, don't forget to head over and subscribe to my channel, and I'll see you in the course. Hey everybody, and welcome to this Python and OpenCV course. Over the next couple of videos, we're going to be talking about using the OpenCV library to perform all sorts of image and video related processing and manipulations. Now, I won't be delving into what OpenCV really is, but just to be brief, it is a computer vision library that is available in Python, C++, and Java. Now, computer vision is an application of deep learning that primarily focuses on deriving insights from media files, that is, images and video. Now, I'm going to assume that you already have Python installed in your system, and a good way to check this is by going to your terminal and typing python --version. Now, make sure you're running a version of Python of at least 3.7 above. Whatever we do in this course won't really work in some older versions of Python, and especially Python 2. So just make sure that you have the latest version installed. Go ahead to python.org and download the latest version from there. Now, assuming that you've done this, we can proceed to installing the packages that we require in this course. The first one is OpenCV. So go ahead and do a pip install opencv-contrib-python. Now, sometimes you may find people telling you to install just opencv-python. Well, this opencv-python is basically the main package, the main module of OpenCV. opencv-python includes everything in the main module as well as the contribution modules provided by the community. So this is something I recommend you install, as it includes all of OpenCV's functionality. Now, you may also notice that OpenCV tried to install the NumPy package. Now, NumPy is kind of a scientific computing package in Python that's extensively used in matrix and array manipulations, transformations, reshaping, and things like that. Now, we'll be using NumPy in some of the videos in this course, but don't worry if you've never used them before. It's simple and relatively easy to get started with. Now, the next package I'd like you to install is Sierra. So go ahead and do a pip install Sierra. Now, slight disclaimer, this is a package that I built to basically help you to speed up your workflow. Sierra is basically a set of utility functions that will prove super useful to you in your computer vision journey. It has a ton of super useful helper functions that will help speed up your workflow. Now, although we're not going to be using this for a good part of this course, in fact, we'll only begin to use this in the last video of this course when we're building a deep computer vision model, I recommend you install it now so that you don't have to worry about the installation process later on. If you're interested in contributing to this package, or just simply want to explore the codebase, I'll leave a link to the GitHub page in the description below. Okay, so that's it for this video. In the next video, we'll be talking about how to read images and video in OpenCV. So, I'll see you guys in the next video. Hey everybody, and welcome back to another video. In this video, we're going to be talking about how to read images and video in OpenCV. So I have a bunch of images in this photos folder and a couple of videos in this videos folder. In the first half of this video, we'll be talking about how to read images in OpenCV, and toward the end, we'll be actually talking about how to read videos. So let's start off by creating a new file. We call this read.py, and the first thing we have to do is actually import cv2.cv. So the way we read in images in OpenCV is by making use of the cv.imread method. Now, this method basically takes in a path to an image and returns that image as a matrix of pixels. Specifically, we're going to be trying to read this image of a cat here. So we're going to say photos/cat.jpg, and we're going to capture this image in a variable called img. And you can also provide absolute paths, but since this photos folder is inside my current working directory, I'm going to reference those images relatively. Now, once we've read in our image, we can actually display this image by using the cv.imshow method. Now, this method basically displays the image as a new window. So the two parameters we need to pass into this method is actually the name of the window in this case is going to be cat, and the actual matrix of pixels to display, which in this case is engi. And before we actually move ahead, I do want to add an additional line. The cv.wait v0. Now the cv.wait v0 is basically a keyboard binary function. It waits for a specific delay or time in milliseconds for a key to be pressed. So if you pass in 0, it basically waits for an infinite amount of time for a keyboard key to be pressed. But don't worry too much about this, it's not really that important for this course, but we will be discussing some parts of it towards the end of this video. So let's actually save this and run by saying python read.py. And the image is displayed in a new window. Cool. Now this was a small image. This was an image of size 640 by 427. Now we're going to try and read in this image of the same cat, but a much larger version. 2400 by 1600 image. So we're going to say cat underscore large.jpg. Save that and run. And as you can see, this image goes way off screen. The reason for this is because the dimensions of this image were far greater than the dimensions of the monitor that I'm currently working on. Now currently OpenCV does not have an inbuilt way of dealing with images that are far greater than your computer screen. There are ways to mitigate this issue, and we'll be discussing them in the next video when we talk about resizing, rescaling, frames, and images. But for now, just note that if you have large images, it's possibly going to go off screen. So that's it for reading images. We can now move on to reading videos in OpenCV. Let's go reading videos. So what we're going to do is we're actually going to read this video of a dog. And the way we read in videos is by actually creating a capture variable and setting this equal to cv.video capture. Now this method either takes in integer arguments like 0, 1, 2, 3, etc. or a path to a video file. Now you would provide an integer argument like 0, 1, 2, 3 if you are using your webcam or a camera that is connected to your computer. In most cases, your webcam would be referenced by using the integer 0, but if you have multiple cameras connected to your computer, you could reference them by using the appropriate argument. For example, 0 would reference your webcam, 1 would reference the first camera that is connected to your computer, 2 would reference the second camera, and so on. But in this video, we'll be actually looking at how to read in already existing videos from a file path. Now specifically, we'll be reading this video of the dog here, and the way we do that is by providing the path. So videos/dog.mp4. Now, here's where reading videos is kind of like different from reading images. In the case of reading of videos, we actually use a while loop and read the video frame by frame. So we're going to say while true, and the first thing we want to do inside this loop is say is true and frame is equal to capture.read. Now this capture.read basically reads in this video frame by frame. It returns the frame and a boolean that says whether the frame was successfully read in or not. To display this video, we can actually display an individual frame. So we do this by saying cv.unshow, and we call this video, and we pass in the frame. And finally, for some way to stop the video from playing indefinitely, is by saying if cv.wait key 20 and 0xff is equal to port of b, then we want to break out of this while loop. And once that's done, we can actually release the capture pointer and we can destroy all windows. And we can get rid of this. So basically, just to recap, the capture variable is an instance of this video capture class. Inside of while loop, we grab the video frame by frame, by utilizing the capture.read method. We display each frame of the video by using the cv.timeshow method. And finally, for some way to break out of this while loop, we say if cv.wait key 20, if and 0xff is equal to order of d, which basically says that if the letter d is pressed, then break out of this loop and stop displaying the video. Finally, we release the capture device and we destroy all the windows. We don't need them anymore. So let's save that and run, and we get a video display in a window like this. But once it's done, you'll notice that the video suddenly stops and you get this error. Most specifically, a negative 215 assertion failed error. Now, if you ever get an error like this, negative 215 assertion failed, this would mean in almost all cases is that OpenCV could not find a media file at that particular location that you specified. Now, the reason why it happened in the video is because the video ran out of frames. OpenCV could not find any more frames after the last frame in this video, so it unexpectedly broke out of the while loop by itself by raising a CV2 error. And now you can get the same error if we comment this out, we uncomment this out, and we specify a wrong path to this image. So that's CV2 wait key 0, save that and run, and we get the exact same error. This basically again says that OpenCV could not find the image or the video frame at a particular location. Basically, it could not be read. That's what it said. So that's pretty much it for this video. We talked about how to read in images in OpenCV and how to read in videos using the video capture class. In the next video, we'll be talking about how to rescale and resize images and video frames in OpenCV. So see you then. Hey everyone, and welcome back. In this video, we're going to be talking about how to resize and rescale images and video frames in OpenCV. Now, we usually resize and rescale video files and images to prevent computational strain. Large media files tend to store a lot of information in it, and displaying it takes up a lot of processing needs that your computer needs to assign. So by resizing and rescaling, we're actually trying to get rid of some of that information. Rescaling a video implies modifying its height and width to a particular height and width. Generally, it's always best practice to downscale or change the width and height of your video files to a smaller value than the original dimension. The reason for this is because, while most cameras, your webcam included, do not support going higher than its maximum capability. So for example, if your camera shoots in 720p, chances are it's not going to be able to shoot in 1080p or higher. So to rescale a video frame or an image, we can create a function called depth rescale frame, and we can pass in the frame to be resized and scaled value, which by default we're going to set as 0.7. What I'm going to do next is I'm going to say width is equal to frame.shape of 1 times scale, and I'm going to copy this and do the same thing for the height. Now remember, frame.shape of 1 is basically the width of your frame or your image, and frame.shape of 0 is basically the height of the image. Now, since width and height are integers, I can actually convert these floating point values to an integer by converting it to an int. And what we're going to be doing is we're going to create a variable called dimensions and set this equal to a tuple of width, height, and we can actually return cv.resize the frame, the dimensions, and we can pass in interpolations of cv.inter_area. Now we'll be talking about cv.resize in an upcoming video, but for now just note that it resizes the frame to a particular dimension.
Insufficient funds.
So, that's all our function does. It takes in the frame and it scales that frame by a particular scale value, which by default is 0.75.
Construction.
So let's actually try to see this in action. Let's go back to this reader.py and grab this code. And we can paste that there. We don't need images for now.
Building. Cannot deploy here.
I'll comment
Construction
these
complete.
out.
New construction options.
Now what I'm going to do is, after I read in the frame, I'm going to create a new frame called frame underscore resize and set this equal to rescale frame of the frame, and let's leave the scale value as 0.75. And we can actually display this video resize by passing in frame underscore
Enemy
resize.
detected. Select target. Construction. Select target. Enemy
So
engineer
let's save that and run. Python rescale
Allies under attack.
.py. There was an error.
Training.
Okay, we don't need this. Let's close that out. Save that and run.
Cannot
And
deploy here.
this was our original video, and this is actually a resized video. Video resized by 75%. We can modify this by changing the scale value to maybe
Construction.
0.2. So we're rescaling to 20%,
Our ally has placed the beacon.
and we get an even smaller video in a
Enemy
new video.
engineer detected. Cannot deploy here. Building. Unit lost.
So let's close that out.
Construction.
Now you can also apply this on images. So let's uncomment that out. Goes out to cat.jpg. And we can do cd.imshow
Building.
image and pass in the resize
Funds. On hold. Repairing.
image. We can create a resized image
Building.
by
Building.
calling rescale frame, and we can pass in the img. Let's save that in
Unit is
run.
under attack. Beacon
And
placed.
this is a small video, so we're not concerned with that.
Building.
This is actually
Insufficient funds.
the big image, the large image, and this is the resized version of this image. Let's close that out. Now there is another way of rescaling or resizing video frames specifically, and that's actually using the capture.set method. Now this is specifically for videos
Building.
and won't
Unit
work for
lost.
images. So let's go ahead and try to do that. Let's call this
A unit
dev
is under attack.
change
On hold.
res. So we're changing the resolution of the image of the video,
Insufficient funds.
and we can pass in a width and a height.
Construction complete.
And what we're going to do is we're going to say capture.set read, comma,
Our base is
width,
under attack.
and we're going to do the same thing with capture.set for comma height.
Building. Construction.
Now 34 basically stand for the properties of this capture class. So 3 references the width and 4 references the height. You can also expand this to maybe change the brightness in the image, and I think you can reference that by setting this to 10. But for now we're going to be interested in the width and the height. Now, I do want to point out this. This method will work for images, videos, and live video. Basically for everything you can use this rescale frame method. But the change function only works for live video. That is video you read in from an external camera or your webcam, for instance. The video that is going on currently. This is not going to work on standalone video files that already exist. It just doesn't work.
Construction.
So if you're trying to change the resolution of live video, then go with this function. If you're trying to change the resolution of an already existing video, then go with this function.
Building captured.
So that's pretty much it for this video. So we talked about how to resize and rescale video frames and images in OpenCV. In the next video, we'll be talking about how to draw shapes and write text on an image. So that's everything. I'll see you guys in the next video.
Cannot deploy here.
Hey everyone, and welcome back to another video. In this video, we're going to be talking about how to draw and write on images. So go ahead and create a new file and call this draw.py.
A unit is under attack. Enemy
We're going to
engineer
import
detected.
cd2 and
Construction
cd3.
complete.
We're going to
Cancel.
import the numpy package that OpenCV has installed previously,
Complete.
and we're going to import that as np.
A
We
collector
will read
is
in
under
an image
attack.
by saying unread equals to cd.imread, pass in photos/cat.jpg,
Our base
and
is
display
under
that
attack.
image in a new window, and we can do
Insufficient funds.
cd.weight 0.
Cash bounty.
Now there are two ways we can draw on images. By actually drawing on standalone images like this image of a cat here, or we can create a dummy image, a blank image to work with. And the way in which we can create a blank image is by saying blank is equal to np.0 of shape 500 by 500 and give it a data type of uint8. uint8 is basically an image, the data type of an image.
Building.
So if you want to try and see this image, see what this image looks like,
Insufficient funds.
you can say blank and you can pass in blank. Save that and run.
Orbital
Python
ready.
draw.py. And this is basically the blank image that you can draw on. So we're going to be using that instead of drawing on this cat image. But feel free to use this cat image if you like. So the first thing we're going to do is try to paint
Enemy engineer
the image
complete.
a certain color. And the way we do this is by saying blank and reference all the pixels and set this equal to 0,255,0. So by painting the entire image green. And we can display this image by saying green and passing the blank image. Save that and run.
Unit lost.
And broadcast. Yeah. Okay, you need to give it a shape of 3. Basically, we are giving it a shape of height, width, and the number of color channels. So just keep that in mind. Save that. And this is the green image that we get. Cool. We can even change this and try to change this to red. 0,255. Save that. And we get a red image over here. Now, you can also color a certain portion of the image by basically giving it a range of pixels. So we can say 200 to 300, and then from 300 to 400. Save that and run.
Mass production
And you got a red square
authorized.
in this image.
On hold.
The next thing we're going to do is we're going to draw a rectangle. And the way we do this is by using the cb.rectangle
units detected.
method. And this method takes in an image to draw the rectangle over, which in this case is blank,
Building.
and it takes in point 1, point 2, color,
Building.
thickness, and a line type if you like. So the point 1 will specifically be 0,0, which is the origin, and we can go all the way across to 250, 250.
Insufficient funds.
Let's give it a color of 0,255,0, which is green. Give it a thickness of, let's say, 2, which is basically the thickness of the borders. And once that's done, we can display this image by saying, let's call this rectangle,
Insufficient
and
funds.
passing
Construction
and passing the
complete.
blank
Enemy
image.
has been defeated.
We can comment this out since we don't
A
need this
unit is
anymore.
under attack. Construction.
And we get a green rectangle that goes all the way from the origin to 250, 250. We can play around with it if you like. So this is going from 250 to maybe 500. And it goes all the way across the image. So you basically divide the image in half.
Enemy engineer detected.
Now there is a way of filling in this image a certain color. And the way we do this is instead of saying thickness is equal to 2, we say thickness is equal to cb.fill.
A unit is under
And that
attack.
basically fills in the rectangle to get this green rectangle. Now alternatively, you can also specify this as name 1.
Our ally is under attack. Our base is under attack.
And we get the same result. What we can also do is instead of giving it fixed values like 250 and 500, what we can do is we can say ing.shape of 0 of 1 divided by 2, and image dot shape of 0 divided by 2. Let's save that and run.
Unit lost.
Image not fact card.
Our ally
This is
is under
blank.
attack.
And this is blank. Save that and run. And we get a nice little rectangle, or square, if you will, in this image. What it basically did is it scaled the rectangle from, instead of being this entire square, this rectangle basically has dimensions half of that of the original image.
A unit is under
So
attack.
moving on, let's try and draw a circle.
Building. Our
Draw
ally is
a
under
circle.
attack.
This is also fairly straightforward. We do a CV dot circle, and we pass in the blank image, and we give it a center, which is basically the coordinates of the center. And now let's set this to the midpoint of this image. By saying 250, 250.
Complete. Construction.
Alternatively, you could also get
Our
this.
unit is under attack. Cannot deploy here.
Let's give it a radius of 40 pixels, give it a color of 0,0,255, which is red, BTR, and give it a thickness of, let's say, 3.
Our ally is under attack. Unit lost.
We can display this image, say,
Building. An
circle
orbital
is equal to black.
Building. Cannot deploy here. Building. A unit is
And we get a nice little circle over here
ready.
that has its center
Cannot
at
deploy
250,
here.
250, and a radius of 40 pixels. Again, you can also fill in this
Cannot
image
deploy here.
by giving it a thickness of -1.
Construction.
And we get a nice little dot here in the middle. Cool.
Ally is under attack.
Now there's something else that I forgot, and that is how to draw a line, a standalone line on the image. That again is fairly straightforward. We use the CV dot line method, and this takes in the image to draw the line on, and 2 points. Let's just copy these points. Everything. And this basically draws a point from 0,0 to half of these image dimensions, so that's 250, 250, and then it draws a line of color 0,255,
Building.
let's set this to full white, 255, 5 and 255, and basically the thickness you can specify as 3.
An ore mine is nearing depletion. Building.
Now we can display this image. You go on show, call this line,
Our base
Your
is
mark.
under attack. Building.
blank image.
Our ally is under attack.
And we get a line that goes all across from 0,2, 0,0 to 250, 250.
Complete. Training.
Let's try and play around with this. Let's draw a line from 100 to maybe 250. And then it goes all the way to 300
Is under attack.
to 400. Save that from. And you get a line that goes from 100 to 300, 400. Cool. And finally, the last thing that we will discuss in this video is how to write text on an image. So that's write text on an image.
Asha.
Now the way we do this is very straightforward. We do a CV dot put
Ally is under attack.
text,
Our base is under
and
attack.
this will put text on the blank image.
Building.
We specify what we want to put on.
Building.
So I say hello.
Building.
We can do an origin, which is basically where we want to draw the image from. Let's set this to 225 and 225. And we can also specify
Engi engineer
font
detected.
face. Now OpenCV comes with inbuilt font faces, and we will be using the cv.font_Hershey_, we'll be using the triple X. You have complex, you have duplex, you have plain, you have script simplex, and a lot of inbuilt fonts. But for now, let's use the triple X. Let's give this a font scale, which is basically how much you want to scale the font by. Let's set this to 1.0. which we want to scale
An
upon.
ornament has been depleted.
Let's give it a color of 0,255,0 and give it a thickness of 2.
Orbital downpour ready. We
So
lost a collapse.
and
Our base is under
comment that
attack.
out, and we can display this image. So see down and show, let's call this text and pass in the blank image. And we get some text that is placed on the image. We play around with it and say, hello, my name is Jason.
An ore mine is nearing depletion.
Save that and run. And it goes off screen when we're dealing with large images, but we can, there's no way of actually handling this except for maybe changing the margins here a bit. We can do that by saying 0,225.
Cannot deploy here. Construction complete.
And it starts from 0 and says blue ranges.
Building.
So, that's it for this video. We talked about how to draw shapes, how to draw lines, rectangles, circles, and how to write text on an image. Now in the next video we'll be talking about basic functions in OpenCV that you're most likely going to come across whatever project in computer vision you end up doing. So if that's it, I'll see you guys in the next video.
Unit lost.
Hey everyone, and welcome back to another video.
Cannot deploy here.
In this video, we're going to be talking about the most basic functions in OpenCV that you're going to come across in whatever computer vision project you end up building.
Construction
So let's start off with the first
Our base
function,
is under attack.
and that is converting an image to grayscale.
Ally is under attack.
So we've written an image and we displayed that image in a new window, and currently this is a BGR image. Our ways in OpenCV to essentially convert those BGR images to grayscale, so that you only see the intensity distribution of pixels rather than the color
Our
itself.
base is under attack.
So the way we do that is by saying gray is equal to cv.cv3.
Ally is under attack.
We pass in the image that we want to convert from, which is img, and we specify a color code. Now this color code is cv.color_BGR to gray, since we're converting a BGR image to a grayscale image.
Building.
And we can go ahead and display this image. cv.show
Complete. A unit is under
pass in
attack.
gray and pass in the gray image. Save that and run.
Building.
The Python basic.py. And this was the original image, and this is the grayscale image. Let's try this with another image. But with the image of the park in Boston. And this is the BGR image in OpenCV, and this is its corresponding grayscale image.
Our base is under attack.
So nothing too fancy, you just convert it from a BGR image to a grayscale image. The next function we're going to discuss is how to bad lighting when the image was taken, or maybe some issues with the camera sensor and so on. And some of the ways we can actually reduce this noise is by way too many noise techniques, which we will discuss. But for now, we're just going to use the gaussian. What we're going to do is we're going to create a blurred image, as in blur is equal to cv.gaussian. And this image will take in a strings image, which is the img. It will take in a kernel size, which is actually triplet, which is basically the window size that OpenCV uses to compute the blur image. We'll get into this in the advanced part of this code, so don't worry too much about this. Just know that this kernel size has to be an odd number. So let's start off real simple and keep the kernel size to 3 bytes. And another thing that we have to specify is cv.border_default. So go ahead and try to display this image, say blur, and pass in blur. Now you will be able to notice some of the differences in this image, and that is because all of that is colored, right? The people in the background are pretty clear in this image, and over here they are slightly cleared up. To increase the blur in this image, we can essentially increase the kernel size. So from 3x3 to 7x7. Save that and run. And this is the image that is way more blurry. So, that's it. The next function we're going to discuss is how to create an edge cascade, which is basically trying to find the edges that are present in the image. Now, again, there are many edge cascades that are available, but for this video we're going to be using the canny edge detector, which is pretty famous in computer vision world. Essentially, it's a multi-step process that involves a lot of blurring and then involves a lot of grading computation. So we're going to say canny is equal to cd.canny. We pass in the image. We pass in two threshold values, which for now we're going to say 1.5 and 175. Let's go ahead and try to display this image. Go to canny images, and we can pass in canny. Save that as well. And these are the edges that were found in this image. As you can see that there were hardly any edges found in the sky, but a lot of features in the trees and the buildings, and quite a few, features and edges in the grass and stuff. We can reduce some of these edges by essentially blurring them. Do that is instead of passing the ing, we pass in the blur. Save that and run. And as you can see that there were far less edges that were found in here. And this is the way you can basically reduce the amount of edges that were found by a lot, by applying a lot of blur, or get rid of some of the edges by applying a slight blur. Now, the next function we're going to discuss is how to dilate an image using a specific structuring element. Now, the structuring element that we are going to use is actually these edges, the canny edges that were found. So we're going to say dilating the image. And the way we do that is by saying dilated is equal to cd.dilate, and this will take in the structure, which is basically the canny edges, and it will take in the kernel size, which we'll specify as 3x3 for now, and it will also take in iterations of 1. Now, dilation can be applied using several iterations at a time, but I'm going to stick with 1. So go ahead and try to display this image by saying cd.unshow, call this dilated, and we can pass in dilated. So that and if these were our edges, these are the dilated edges. We can maybe increase the kernel size to maybe 7x7 and try to see what that does. And nothing much was done. Not much difference was that. Let's try to increase the number of iterations to 3. And it's definitely way thicker. But you're going to see subtle differences with the amount of features and edges that you find. Now there is a way of eroding this dilated image to get back this structuring element. Now it's not going to be perfect, but it will work in some cases. So we're going to say, call this eroding, and we call this eroded is equal to cd.erode. It will take in the dilated image, pass in dilated. It will take the kernel size of, let's start off with 3x3, and give it iterations of 1, just for now. And we can display this image. Show course was eroded. And if this was your structuring element, and this was your dilated image, this is basically the result you get from eroding this image. Now it isn't the same as a structuring element, but you can just about make the features there. But you can see that between this and this, there is a subtle change in the edges, the thickness of these edges. We can maybe try to match these values so that we attempt, so that there is an attempt to get back this edge cascade.
Our base is under attack. Our unit is infected.
Yes, we got the edges back. So as you can see that compared to these two, they look pretty much
Our
the
ally is
same.
under attack.
Yeah, the edges are the same. So essentially, if you follow the same steps, you can, in most cases, get back the same edge
Our
cascade.
line is nearing depletion.
And probably the last function that we're going to discuss is how to resize and crop an image. So we're going to start with resize.
Our base is under attack.
So we covered resizing video frames and images in the previous video, in one of the previous videos.
Construction complete.
But we're just going to touch on the cv.resize function just a bit. So we're going to say resize equal to cv.resize. This will take in an image to be resized, and it will take in a destination size, which let's set this to 500 by
Our ally
500.
is under attack.
And so this essentially takes in this image on the part and resizes that image to 500 by 500, ignoring the aspect ratio.
Unit lost.
So we display this image by saying cv.unshow resize and resize.
Cancel.
Save that,
New
right.
construction options.
And let's go back to this image. If this is the original image, this is the image that was resized to 500 by 500. Now by default there is an interpolation that occurs in the background, and that is cv.inter_area. Now this interpolation method is useful if you are shrinking the image to dimensions that are smaller than that of the original dimensions.
Unit is under
But in
attack.
some cases, if you are trying to enlarge the image and scale the image to a much larger dimensions, you would probably use the inter_linear or the inter_cubic. Now, cubic is the slowest among them all, but the resulting image that you get is of a much higher quality than the inter_area or the inter_linear. So let's touch on cropping. And that's basically by utilizing the fact that images are arrays, and we can employ something called array slicing. We can select the image on the basis of their pixel values. So we can say cropped the image, and we can select a region from 50 to 200 and from 200 to 400. And we can display this image, call this cropped, pass in cropped. And this is the cropped image of, let's go back here, of this original image. If you try to superimpose them, it's probably going to be right over there. Yeah, it's basically this portion. So that's pretty much it for this video. We talked about the most basic functions in OpenCV. We talked about converting an image to grayscale by applying some blur, by creating an edge cascade, by dilating the image, by eroding that dilated image, by resizing an image, and trying to crop an image using array slicing. In the next video, we're going to be talking about image transformation. That's translation, resizing, flipping, and cropping. So if you have any questions, leave them in the comments below. Otherwise, I'll see you guys in the next video. Hey everyone, and welcome back to this Python and OpenCV course. In this section, we're going to cover basic image transformations. Now these are common techniques that you'll likely apply to images, including translation, rotation, resizing, flipping, and cropping. So let's start off with translation. Translation is basically shifting an image along the X and Y axis. So using translation, you can shift an image up, down, left, right, or with any combination of the above. So to translate an image, we can create a translating function. We're going to call this def translate. And this translation function will take in an image to translate and take in X and Y. X and Y basically stand for the number of pixels you want to shift along the X-axis and the Y-axis respectively. So to translate an image, we need to create a translation matrix. So we're going to call this transmet is equal to np.float32, and this will take in a list with two lists inside of it. In the first list, we're going to say 1, 0, x and 0, 1, y. And since we're using numpy, we can import numpy as np. And once we've created a translation matrix, we can essentially get the dimensions of the image, saying dimensions, which is a tuple of image.shape of 1, which is the width, and image.shape of 0, which is the height. And we can return cv.warp affine. This will take in the image matrix, so transmit, and it will take in the dimensions. And with that done, we can essentially translate our image. Now before we do that, I do want to mention that if you have negative values for x, you are essentially translating the image to the left. Negative y values imply shifting it up. Positive x values imply shifting it to the right. And as you guessed, positive y values shifted down. So let's create our first translated image. By setting this equal to translate, we're going to pass in the image, and we're going to shift the image right by 100 pixels and down by 100 pixels. So that's over cv.image translated and translated. Save that and run Python transformations.py. And this is your translated image. It was shifted down by 100 pixels and shifted to the right by 100 pixels. So let's change that. Let's shift the image left by 100 pixels and down by 100 pixels. So we pass in negative values for x. And it moved to the left. Feel free to play around with these values as you see fit. Just know that negative x shifts it to the left, negative y shifts it up, x shifts it to the right, and positive y values shift it down. Moving on, let's talk about rotation. Rotation is exactly what it sounds like, rotating an image by some angle. OpenCV allows you to specify any point, any rotation point that you like to rotate the image around. Usually it's the center, but with OpenCV you can specify any arbitrary point. It could be any corner, it could be 10 pixels to the right, 40 pixels down, and you can shift the image around that point. So to rotate the image, we can create a rotating function. It's called devRotate. This will take an image angle to rotate around and a rotation point, which we're going to set as none. So we're going to grab the height and the width of the image by setting this equal to ing.shape of the first two values. And basically, if the rotation point is none, we are going to assume that we want to rotate around the center. So we're going to say rot point is equal to width divided by 2 and height divided by 2. We can essentially create the rotation matrix like we did with the translation matrix by setting this equal to rot met is equal to cv.getRotation matrix 2D. We're going to pass in the center, the rotation point, an angle to rotate around, which is angle, and a scale value. Now we're not interested in scaling the image when we rotate it, so we can set this to. Finally, we can set a dimensions variable equal to the width and then the height. And return the rotated image, which is cv.warp affine image rot met, the destination size, which is dimensions, and that's it. That's all we need for this function. So we can create a rotated image by setting this equal to rotate, and we can rotate the original image by 45 degrees. So let's display this image, call this rotated, and pass in rotated. Save that and run. And this is your rotated. As you can see, it was rotated counterclockwise by 45 degrees. If somehow you wanted to rotate this image clockwise, just specify negative values for this angle, and it will rotate the image around. Rotated clockwise. Now, you can also rotate a rotated image. That is, take this image and rotate it by 45 degrees further. So let's call this rotated. Rotated, rotated is equal to rotate of rotated. And we can rotate this image by another 45 degrees. So we're rotating it clockwise. And we can cv.imshow, call this rotated, rotated, and we can pass in rotated, rotated, rotated. And this is your rotated image. Now the reason why these black lines were included is because if there's no image in it, if there's no part of the image in it, it's going to be black by default. So when you took this image and rotated it by 45 degrees, you essentially rotated the image, but it introduced these black triangles. Now if you try to rotate this image further by some angle, you are also trying to rotate these black triangles along with it. So that's why you get these kind of a skewed image. So there's additional triangles that are included over here. Save yourself the trouble and basically add up these angles and you will get the final angle. So we can change